In this video, we're going to define the notion of an equivalence relation and give an example. So let's first recall some definitions about relations. First, the definition of a relation. So if A and B are sets, a relation between A and B is simply a subset of the Cartesian product A cross B. Okay? If A is equal to B, and so the relation R is just a subset of A cross A, then we say the relation is simply a relation on A. Now, again, usually instead of writing that some ordered pair is a member of the relation, okay, because R is a collection of ordered pairs, so it would be reasonable to write that A comma B is an element of the relation R if A is related to B. But instead of doing that, we'll usually write A R B and read it as A is related to B. Okay, this is the common practice when it comes to things like the equality relation, the less than relation, and so on. So let's suppose that R is a relation on a set A. We say the relation is reflexive when for all A in the set big A is related to A. Okay, so a relation is reflexive if everything is related to itself. We say a relation is symmetric if whenever A is related to B, then B is related to A. And we say a relation is transitive if whenever A is related to B and B is related to C, then A is related to C. Okay, reflexivity, symmetry, and transitivity all combine together to define what's called an equivalence relation. So if A is a set, a relation on A is called an equivalence relation if it is reflexive, symmetric, and transitive. So here's an example of an equivalence relation. So let's define the relation on Z, on the integers, defined as follows. We'll say that n is related to m if and only if n minus m is even. So n is related to m if and only if the difference between n and m is even. So to prove something is an equivalence relation, you have to do three kind of sub-proofs. You have to prove transitivity, reflexivity, and symmetry. Okay, so first let's do reflexivity. Okay, we need to prove the relation is reflexive, we need to prove that for any integer, n is always related to itself. So we need to prove that n minus n is always even. And of course that's true because if you have an integer n minus n is equal to 0, and we classify 0 as an even number since it's equal to 2 times 0. So n minus n is even for all for all integers n, and so for all integers n is related to n. All right, that shows that this relation is reflexive. Now we have to show that the relation is symmetric. Okay, so to see that the relation is symmetric, let's suppose that we have two integers n and m, and let's suppose that n is related to m. That of course means that n minus m is even. So there is some integer k, so that n minus m is equal to 2 times k. All right, but then of course we can just multiply by -1 and get m minus n is equal to minus n minus m, all right, which is minus 2k. And so m minus n is even as well. It's 2 times -k, and so that makes it an even number. And since m minus n is even, that means that m is related to n. So we've just proved that if n is related to m, then m is related to n. So that proves that this relation is symmetric. Now let's prove that the relation is transitive. Okay, so we've got symmetry. Finally, let's prove that it's transitive. To prove this, we have to show that if we have three integers, m, n, and p, such that m is related to n and n is related to p, then we have to prove that m is related to p. Okay, so let's suppose that we have integers m, n, and p. Suppose that m is related to n, and suppose that n is related to p. So that means, by our two suppositions here, that there are integers j and k, so that m minus n is 2j, and n minus p is 2k. All right, m minus n has to be even, so it's 2 times some integer, and n minus p has to be even, so it's 2 times some other integer. All right, so then we can just easily, with a little algebra, calculate m minus p. We can see that that's m minus n plus n minus p. M minus n is 2j, n minus p is 2k. So m minus p is 2 times the quantity j plus k. Well, j plus k is an integer, so that makes m minus p even, so m is related to p. All right, so this relation we've just proved is reflexive, symmetric, and transitive, and so it follows that the relation is in fact an equivalence relation. All right, so all proofs that a relation is an equivalence relation are going to involve 3 kind of sub-proofs: a proof that the relation is reflexive, a proof that the relation is symmetric, and a proof that the relation is transitive. That's it for this video. Thanks for watching.